And that's still not the end of the story. We're going to look at one more really interesting algorithm that has lots of important applications. It's called the Rabin-Karp algorithm, invented by two Turing Award winners, Michael Rabin and Dick Karp. I can remember hearing about this algorithm from my friend Dick Lipton, who explained it to me over the phone, and he explained it to me in about 15 seconds, and I realized I had to have this in the book, so now here we are presenting it. That was in the 70s. So the basic idea for the Rabin-Karp algorithm has to do with hashing. It's a particular kind of hashing called modular hashing. It's just a particular way of computing a hash function. And it's easiest to think about in terms of numbers, although it works in all kinds of situations because, remember, everything in a computer is encoded as a bit, which can be treated as bits, which could be treated as binary numbers. And so what we're going to do is, in this case, so our pattern characters are decimal digits, say. And so we'll treat a sequence of pattern characters as a decimal number. And modular hashing is just take a big prime and compute the remainder when you divide your number by that prime. So in this case, 613 is the remainder that you get when you divide 26,535 by 997. So you can check that. And so that's what we're going to use as the hash function. And this type of hashing is widely used. You have a prime number. We talked about it when we talked about hashing. It seems to satisfy something like the uniform hash assumption under various circumstances. So that's our pattern, a 5-character pattern, and we're going to keep the small hash value 613. And this is going to generalize to longer patterns, and we'll talk about that in a minute. So now suppose we have this text, and our pattern happens to occur here in the text. And what the method is built on is the idea of you take the first 5 characters in the text and compute its hash value. In this case, 31,415 mod 997 is 508. So that's different, so that's not the pattern. And then you take the next 5 characters, that's 201. That's different, it's not the pattern. Take the next one, that's 715. It's different, it's not the pattern. 15,926 mod 997 is 971, it's not the pattern. Eventually, when you have the text characters that are the same as the pattern characters, you're going to get the same result. It's a match. If the pattern hash equals the text substring hash, you have the potential for a match. That's what the algorithm's based on. Now it seems like we're doing a lot of calculation with making numbers out of these things and doing modular arithmetic on it. But actually there's a really simple way to severely limit the amount of calculation and give a quick linear algorithm for search, substring search. So first thing is how to compute the hash function. So if we take convert to math, so R is our radix, so in this example we're using 10, so we have decimal numbers. And then the digits, say T sub I, that's the text characters. So we have a number, X sub I, which is the M characters starting at position I. And that's just, in math, T sub I times R to the M minus 1. So, in this case, that's 2 times 10,000 plus 6 times 1,000 plus 5 times 100 plus 3 times 10 plus 5. That's just math for that. And our goal is, so it's an m-digit base R integer modulo q, and our goal is to do the math to give us the remainder that we would get when dividing that by q. There's a really easy method called Horner's method that we can use to evaluate a degree m polynomial just with a m multiply and adds. And we can do the modular computation all the way through at each step to keep the numbers less than q, and we still get the same result. And so the idea is you multiply by r, you go from left to right through the digits, and you just multiply by r and add the digit and then do mod q at every time. So we start with 2 mod 97 is 2, 6 mod 987 is 2 times 10 plus 6 mod 987, and that's 26. And then you take that value, multiply by 10 and add 5, that's 265 mod 997. In that case, it's 265. So 265 times 10 plus 3 is 2653. Remainder you divide by 987 is 659. So even though our number gets bigger than 997 by taking them out every time, we keep our running total less than 997. And then the last step is to take the 659. Basically, we've thrown out a bunch of multiples of 997 that we don't care about. And 659 times 10 plus 5 mod 997 is exactly equal to 26535 mod 997, and that's 613. That's our value. So that's using Horner's method, we get a well-known linear time method to compute our hash function with this simple code. And this notice will work even for a huge key that we wouldn't convert a 100-digit key into some number to do the calculation. We do them one digit at a time using Horner's method, and then we have no limit because we're always keeping our numbers less than our prime q. So that's a first step. So no matter how big the pattern is, we can efficiently compute a hash for it. So that's the first step. So now the second step for the Rabin-Karp algorithm is to realize that if we know xi mod q, we can efficiently compute xi plus 1 mod q because they have a lot of digits in common. And you can just do a little math to get to xi plus 1. You take xi, we don't care about the first digit anymore, so you subtract it off, multiply by r, and then add the new digit. That's like one step of Horner's method. And then you have to take that computation, and you can do mod q all the way through. All you have to do is pre-compute r to the n plus 1 mod q. And so here's the computation for one example. If we're at this position 41592, and we know 41592 mod q, we can compute 15926 mod q by subtracting off 40,000, that's TIR the n minus 1, and that gives us just the 4 digits, multiply by the radix, add the new trailing digit, and that's the new value. And if we just keep that all mod q, then we can, with just a multiply and an add at each step, we can keep a running total of the modular hash value of the 5-digit thing. So for example, this is the case that we just did. 4152 mod 997 is done by exactly as we said. We subtract and then add and then multiply by the radix mod 997. So doing those calculations all the way through the search, we eventually get to a match. That's again remarkably small amount of code. We want to keep a long random prime, just keep it a little smaller than the biggest long value to avoid overflow. So we pre-compute r to the n minus 1 mod q because that's the little calculation that we have to do. We compute the hash function, for the pattern. And then with those pre-computations, the search is extremely straightforward. So we take our current hash value, and this is just add a Q to make sure it's positive, and subtract off RM times the first character, and then add in the next character, mod Q. And that gives us the text hash for the current position, and then we compare to see if that's equal to the pattern hash. Now, this is an introduction to the idea of randomized algorithms. There's two ways to proceed from here. One way, called the Monte Carlo version, where we guarantee that the algorithm is going to be quick, but with low probability it might get the answer wrong. In that version, we don't ever bother to check whether go through and check all the digits to see if there's actually a match. We take Q large enough so that we're confident that the probability of two Q-digit numbers or two M-digit numbers having the same hash value is so low that we're not going to worry about it. That's called the Monte Carlo version. The Las Vegas version is guaranteed to get the right answer. In that one, we would go and check to make sure that the M characters match if we have a hash match. And then if it could be that with such a low probability, it could be that there's a hash match but not a substring match, and then we just move on. And from a theoretical point of view, there's some very extremely low possibility that that one could be slow, but let's look at what the analysis says. So the theory says that if you take a sufficiently large random prime, say mn squared, and so a long value, maybe you can get that. And remember, n is huge. Then the probability of a false collision is about 1 over n. So in a billion things, you might get 1 over n. You might get a false collision. So in practice, we choose actually Q just to be there's no reason not to choose as large as we possibly can, not related to M and N. And then the probability of collision is going to be about 1 over Q. So we're going to take it to be like the biggest long. And that means that the probability of collision is extremely small. And then you can take your chances. You can do a Monte Carlo version where you just say, I got a match because I got a hash match, and be confident in the laws of probability, and not worry about the client getting a wrong answer. Or you can have the Las Vegas version where you go ahead and return the correct answer, and be confident that your client's not going to run into a slow case because the probability is so tiny, 1 over Q, that you don't have to worry about it. That's the Rabin Karp algorithm. Now, why look at this algorithm? It's linear time. We have other algorithms that are linear time. One of the key reasons to be interested in Rabin Karp is that it's easy to extend it to more complicated situations. So say you want to look for one of several different patterns. Well, you just compute the hashes for those patterns and then look for any one of them. Use a symbol table to look for them. So that's a much more general capability than we can provide with the other methods. It also can be extended to do two-dimensional search and other things like that. For straight substring search, it's going to be a little slower because there's inner loop is kind of long. The arithmetic operations are going to be a little slow. If you want to do the Las Vegas version, you'd have to back up in the text, and you have this Monte Carlo Las Vegas thing. And you should think about writing code to extend it to look for any one of P possible patterns. That's an interesting algorithmic puzzle that, as I mentioned, is not so difficult to solve. So here's our summary. We started with a brute force algorithm, although typically you don't have this worst case thing, it works fairly well for typical cases. And then we've got the Knuth-Morris-Pratt method that can guarantee linear time and has no backup, and maybe uses extra space unless you use Pratt's version. And you get Boyer-Moore, who can get the running time down to n over m, which is quite an amazing jump and quite useful. And then the Rabin Karp that's very flexible and extends to all these other situations. This is a nice microcosm of algorithmic technology where really interesting and unique and path-breaking algorithmic ideas give us good algorithms for even such a simple problem. That's an introduction to pattern matching.